So today we're going to introduce projections and coordinate systems. This is really the backbone of mapping. And it's really easy to ignore because you bring in shapefiles into ArcGIS and everything's kind of happening in the background. ArcGIS does what's called mapping on the fly. And what that means is when you bring in a shapefile, it's got a bunch of other files associated with it. One of them is a projection file, .prj, not to be confused with a project file in some other program. Arc reads that, knows what to do with it, and plots it. So you can bring in something that has, say, Latin long coordinates. You can bring in something that has northern and eastern coordinates. And Arc, if it has a projection file, will read that and plot everything more or less where it should be. So it's often when you work in GIS easy to ignore projections and coordinate systems because of that kind of ease of use. But we're going to dig into the details, and it's very important because especially in a civil engineering standpoint, when we do mapping, surveying, knowing what projection you're working in and translating that data into a CAD file, communicating a survey from one person to the other, and then also working on historic data. So you've got a topo survey from 5 years ago, you know, what coordinate system was it surveyed in, what vertical datum, so that you can compare it directly to where you're working now. So this really gets into surveying and topography in an important way. So today we're going to compare and contrast different types of projections, datums, and coordinate systems. We'll also define those, right? We'll identify them in GIS data, and we'll convert among them. So you can go from one to another using math. So what are we doing here? What are projections and coordinate systems? They are creating a 2D representation of a spheroidal planet, right? Our planet is round. If you look out at the ocean, the horizon exists at around 30 miles or 32 miles, something around there. And if you watch a boat, I think it was some of the early explorers would watch and see ships coming in from the horizon. The first thing they would see with their scopes are the masts, and then they'd see the whole body of the boat as it came around the curve of the Earth. So you can actually see that, and that's what led to the whole idea that the Earth was round. Probably other stuff. I think the astronomers had something to say something about it as well, but that kind of helped dispel the flat Earth theory, which unfortunately still exists. They like their GPS, but they'll still argue that the Earth is flat. So globes are large and cumbersome to carry around. That's why we have flat paper maps that we can roll up and also display on a screen. Scale and detail is really important, so we need to be able to zoom in and look closely at, you know, a plot level thing. So that's why we have kind of flat maps. And we also need to measure, and it's easier to measure over a flat area than it is a curved area. So we do have spherical coordinate systems, latitude and longitude, as you're familiar. But you can only measure angles in degrees, right? So you have to do spheroidal trigonometry, or whatever you want to call it, geometry, to actually get distance, lateral distance. And so it's not measuring lateral distances in areas is not as straightforward in spherical systems. So we often deal with gridded Cartesian systems. And that's what this is, a gridded system, a Cartesian system, X and Y. And you can have an arbitrary coordinate system where you establish 0, 0 somewhere, you know, maybe on the corner of a property or outside of the boundary. And of course, you probably did this in your surveying class with Professor Krohn, measured and create arbitrary coordinates. We're going to go 100 feet this way, easting, and then 200 feet northing, and then we're going to maybe survey the corners of buildings or property lines based on that. So this is an arbitrary coordinate system. But GIS data typically use standard coordinate systems. So it's a coordinate system that I know if I use this coordinate system and give you a northing and easting, an X and a Y coordinate, and you have data in the same coordinate system, we're going to be able to compare it directly and bring it in on the same map. So coordinate systems, there's many different types. You could imagine if we have vector data, points, lines, or polygons, all those points are going to have X, Y values. Raster data, which we'll talk about a little bit later, has an X and Y location for one corner, usually the top left corner. So we know the coordinate of that. And then we know how many rows and columns there are and what is the spacing and the gridded spacing of those. So if you have one coordinate from the top left, and then you know all the how many X's or how many rows and columns you have, then you can plot that raster in 2D space. So it's basically just kind of pinning it to a spot. This is called georeferencing. Georeference refers typically to rasters, images, but really any spatial data. If it has a georeference, it has a coordinate system. So for example, we'll deal with some aerial imagery in a little bit that is taken from an airplane, maybe in the 1960s, and we want to compare what's changed. I always look at historic aerial imagery to look how rivers change over time. And so I kind of trace the river was over here, and then it migrated over here over so many decades. And often that imagery doesn't have any georeference. It's just a JPEG or a TIFF or a bitmap, something like that. And so there's a process which we'll do together probably in October or November, where you can bring that image in and kind of just drag it in and drape it over an area that you know where it is. And then georeference it by finding points on the image that are located with known spatial points on a georeferenced image. So you can take an image and georeference it and give it and find this essentially this XY location. You're going to stretch it maybe and distort it a little bit. All right, so there's a lot of vocab here. It's going to be important to keep track of all the vocab. Because we're going to revisit it, and there is a quiz at the end of, I think I'll probably end up posting it next week. I'll double check on that, but this is also in the reading, so just so you know, you can reference that as well. So we're gonna talk about projected and unprojected coordinate systems. So unprojected, also known as geographic. And let me kind of just draw a distinction here. Coordinate systems are numbers, right? Lat, long, X, Y. That's typically the two kinds of coordinate systems we have. Coordinate just means we kind of have a pair of numbers that tell you where you are in space. Within coordinate systems, we have unprojected, and these are based on spherical coordinates. And a projection, remember, is taking a sphere or spheroid and flattening it out. That's a projection. We'll get into what that actually looks like in a little bit. But you can see right here, this is an example of a projection. We say project because it's like shining a light. If we had a light bulb in the middle of our spheroid of our Earth and trace these rays of light out over, in this case, a cylindrical flat piece of paper, this would be your projection. And you've seen maps like this. I'm not going to remember the name of it, but you've seen global maps that look like this. So a projection is taking a three-dimensional object and making it two-dimensional. Of course, we have spherical coordinate systems, lat and long, and then we have projected coordinate systems, taking spherical coordinates and making them planar on flat pieces of paper like maps. Using a set of mathematical equations to basically simulate these rays of light coming out of the sphere. And then we go from 3 dimensions to 2 dimensions. As you can see, there's some distortion, right? Not everything's going to be the same. So we'll talk about that in a second. So unprojected and projected. I already hinted at this, but what's the shape of the Earth? It's flat. Yes, Edgar, hold on to that. It's round. Is it a perfect sphere? What's that? So ellipse is flat. And then when you make it three-dimensional, what do you call it? What'd you say? An egg. The Earth is shaped like an egg. This is going to be the new conspiracy theory. All right, so it is ellipsoidal. Well, an ellipsoid is the kind of best. It's really lumpy, right? So it's not a perfect ellipsoid, but we'll look at what that is in a second. Here are spherical coordinates. We have parallel to the equator, also known as latitude. These are our y values. It's always been counterintuitive to me because the parallels go around the planet. If we orient the planet north and south in space, they go around like a belt, but they tell you where you are in the y direction, right? In the quote unquote northern or southern direction. So just important to remember, latitude, equator is 0 degrees latitude. This is north, latitude north, and then latitude south, positive, negative. Then we have our longitudinal lines. The prime meridian is 0 longitude. Do you know where that goes through? It goes through, I think it's England. Yeah. And they were the masters of the sea, right, with all their ships. And I think I'm assuming that they created this and had it go through their country. So very, very, yeah, right through the king's throne. So that's 0 degrees longitude. We're actually in the negative longitude over here. So we're negative 108, 109. Yeah.
So like when you check these 80 point origin, is that like a 0 longitude?
Yeah, exactly. Oh, sorry. So when you go from 3D to 2D, yeah, so we'll talk about that. Often it's an arbitrary point in space outside of the area that we're interested in. So you always have a positive number, and we'll look at that. That's a really great question. So for example, there's a coordinate system. There's 3 planar coordinate systems for Colorado that stretch across, that kind of divided up into 3 layers. And 0, 0 in those planar 2D systems is actually like somewhere in Arizona or New Mexico or something like that. And the whole point is you want to have like big numbers. And so everything's like 100,000 to 1 million northing and easting feet or meters. We'll look at that in a second. So we have positions on the globe, and everything is essentially a vector with degrees east and north or west and south from the center of the planet. And of course, 0, 0 is at the equator and this prime meridian. So here's an ellipsoid. And instead of a sphere, now we have a semi-major and semi-minor axis. And so it is an egg, very subtle egg. And here are the semi-major and semi-minor axis values. And you can see they're actually pretty close. So this is, let's see here, 6,300,078 meters A, and B is 6,300,056,000 meters. So not that far off, right? We're looking at, what is that? 20,000 meters, 22,000 meters difference. And so that means that the Earth is just a little bit wider than it is tall by 22,000 meters or 22 kilometers. So, and do you know why that is? Why is it a little bit egg-shaped? Yeah, it's in centrifugal forces. It's spinning around the North Pole essentially. And so everything's just a little bit stretched out. These have been measured to pretty high levels of precision. You can see we're out here in the 100,000ths of a meter. Based on ground surveys, benchmarks, satellites, we've had a whole network of kind of permanent benchmarks and GPS information that's allowed us to do that. And this is based on what's known as the World Geodetic System 1984. So anytime you see WGS 84, this is an ellipsoid. It has latitude and longitude associated with it. And it's a world unprojected coordinate system. So here's a sphere, here's a spheroid or an ellipsoid. We also have what's called a geoid, and this represents the actual shape of the planet. We'll spend some time in geoids when we talk about GPS surveying. But just know that a geoid essentially represents where sea level is across the planet, which is really lumpy because of gravity, gravitational anomalies. The Earth is more dense in some areas and less dense in others. And we'll talk about it in about a month. So what we do then is we fit this ellipsoid to the actual shape of the Earth as best as we can. It's not going to be a perfect fit. And it's going to be a little bit off, like the center, the blue, if the blue is our ellipsoid and it has a center, the actual center of the Earth is going to be a little bit off from that because we're trying to fit it to the whole planet. And when we fit the shape to the planet, it's called a datum. So a datum is, there's actually going to be different meanings of datums, but when we talk about a coordinate system datum, we're talking about fitting a shape to our planet. And that sets, basically the artificial fit origin. That's going to be the datum of the planet. So and a datum is, in this case, an approximation for the shape used for mapping. This ellipsoid is shifted relative to the geoid, which is our planet, to achieve the best fit. That's a global datum, right? We're doing the whole shape to the whole planet. There's also local datums, and we'll learn about that. There's a North American datum where they fit that ellipsoid so that it matches best up with North America. And that's going to be a little bit different than the global one. So to put a finer point on it, this is a horizontal datum that we're talking about. We'll talk about vertical datums later. So if we look at this blue one, this would be a global fit for the whole planet. If we look at the red one, this would be a local fit. For example, North American datum, right? And so if North America is on this side of the planet, we're going to fit it so that it best fits with this curvature over here. And that's going to be more accurate representation of the surface around North America. So to summarize, we have global horizontal datums and local horizontal datums. And note that the actual center of the Earth is misaligned with the centers of these datums. So here are three that you'll see. And here's an old, has anyone been up Bierstadt? So they put a USGS, I haven't either, USGS marker that gives you the elevation here. And so they surveyed that in. And when you go to USGS maps, a lot of the elevations are going to be in what's called the North American datum in 1927. It's a local datum. It's based on 26,000 surveyed benchmarks across North America. It's been updated in 1983. They brought in over 100 times more benchmarks and as well as satellite data. This datum is updated as the North American continent drifts. So it kind of tracks North America. It's only 2 meters off the actual center of the Earth. Not too bad. And then you have the World Geodetic System, WGS 1984. This is the standard GIS coordinate system. It's an ellipsoid. So anytime you get a GPS Latin long point from your phone or a handheld GPS unit, it's going to give you this information that's based in this horizontal datum. It's 2 centimeters off the Earth's center. There are a bunch of kind of projections that reference this. We'll talk about that later for GPS stuff. Here are the what's called continuously operating reference stations across North America. And so these are GPS antennas that are permanently installed, and they're tracking the movement of the continent over time and giving us a really accurate representation of where this particular point is. So every projection has an underlying geographic coordinate system, a GCS. Projections that are based on different datums will not line up. So we care about datums, they're really kind of under the hood, but they influence our projections. And so what we're seeing here is a road network that has a datum of 1927, North American datum of 1927. And then here's the imagery based on the more updated one. And you can see there's a big offset, and that's pretty significant there. We're talking about hundreds of feet of an offset. So it's really important to understand what datum, horizontal datum, is behind your projection, your coordinate system.